Hey everybody, I wanted to go over the mechanics of using TensorFlow for Scala. Not considering any of the machine learning aspects, this library is still really useful for just doing numerical processing in Scala. It's a really nice interface to TensorFlow. The author of this library is continuing to work on it, and he's even introduced TensorFlow 2 support recently. So very exciting, very nice library, reminiscent of TensorFlow in Python. Even if you don't know TensorFlow in Python, I think you find that this is a very nice library for numerical processing. We'll go over using this for numerical processing, starting with comparing it against using the Scala standard collections, which are very accessible, easy to use, and of course they come with the standard library. I'm going to be doing this in the Ammonite shell. I'm going to start off with a prefix in the Ammonite shell, which I'll include a link in the description to, and you can see it here. This adds in TensorFlow Plotly, which we'll use later, as well as a pretty printer for tensors to the REPL. I'm going to use Ammonite in the terminal. You could also do this in Almond in a Jupyter-style notebook, but we're going to do that later. Here I've loaded that same predef into the Ammonite session already. And what we're going to do is talk about numerical operations on large blocks of scalar data. Tensors are really good at multidimensional scalar data, and you could emulate these using the standard collections. We're going to start with doing what's actually not a very big array of numbers, but it's going to be big enough to demonstrate the point here. We're going to imagine our data set has this many elements in it, and if this was a floating point data set, and we're using 32-bit floats, it's 4 bytes per float, and how many megabytes is that going to be? 64 megabytes. Not too exciting, so really not that big. It's going to be big enough to demonstrate the difference here. So what I'm going to be doing now is I want to have two 64-bit vectors, one using the standard collection and one using TensorFlow, that are using the same data. I'm going to use TensorFlow to initialize this. Otherwise, it takes a really long time. You'll just have to trust me on that. I don't really want to use the standard library for doing this, but you could do this in the standard library. You use like fill, and then you use random next float. So here we have our 64 megabyte array of floats initialized randomly, and I want those as an array of floats. We could use vectors or seq otherwise, but we'll just start with arrays. And in this case, I'm just going to get a copy of that array from TensorFlow. So now these are going to be both initialized to the same data, which we can verify by checking the scalar representation of that element in T0 and V0, and they are the same. So now we have both T0 being a tensor with the same data as V0 being an array. Using our standard Scala collection library, there's ways we can do a variety of manipulations on this. And let's imagine we're doing a hypothetical algorithm that creates a new array of data from the prior array plus some operation. In this case, we're just going to add 12 to every single element. And as we wait for this is pretty straightforward expression for this. We're mapping the function of adding 12 to every single element in V0. And sure enough, we get back V1, which is that result. Then imagine we want an aggregate of this, such as the sum. So let us take that. Again, wait a bit. And we get back the sum. Fairly straightforward, right? Not too bad. We've allocated our data, we've done some manipulation, we've taken our aggregate, all good so far. Let's ask a somewhat of a trick question. How confident are you in this sum being accurate? Scala did what we would consider the standard summation algorithm, which is you have an accumulator, and then over every single value in your array, you're adding that value to your accumulator. We could do this with a fold or other mechanisms, but it's pretty much this, how it's implemented in the standard library. And that gives us our sum. So what is wrong with this? And the long and short of it is that, and in doing our algorithm like so, we are losing precision in our numbers as we're adding them along. This is how the standard Scala collection implements it. And we can imagine a contrived case, where imagine we have S being our current summation, and this is some largest value with a few decimals. We have V, which is a smaller value with a bunch more decimals. And then our new sum, so of course our prior plus V. Now let us consider S minus SP against V. They should be the same. In real numbers, knowing what we know for the laws of arithmetic, we've taken SP, we've subtracted it from both sides, S minus SP equals V. Yet, we're told that's not true. That S minus SP and V are different values. And in fact, we can see here that S and SP have a difference of 0. What has gone wrong here? The answer is, of course, in that floating point is approximate. Doing this throughout all of these values, that's a lot of precision that is lost in this summation. So how do we resolve this? Well, the answer is typically an algorithm like this, where we track a residual, which is the difference between these two as we're doing our summation, and then add that residual back in at the end. So that looks something like this. Again, much the same, summing every single one of our values to S, but we're also adding to our residual the difference between the value we just added to S and what we would expect from the laws of arithmetic to be the value of V. If this was in real numbers, this would always be, there would be no difference here. So this would always be 0, but it's not. Okay, so then we do that. Again, wait a bit. Still waiting. Alright, and our final result is S plus R. So this is a more accurate result of the sum than what the Scala standard library gave us. So let's look at what this looks like in TensorFlow. Already we've talked about, we have T0, which is the same data as that array that we were working on. And we can imagine a hypothetical algorithm where we're adding, doing some operations on T0. In TensorFlow for Scala, we see a nice usability improvement where we have a nice operator for adding a scalar. So we have some nice usability improvements there. We want the sum, and we get back the sum here. And in fact, if we look at the scalar value of that sum versus the value we got using the residual mechanism, we know these are just about the same. Not sure what algorithm TensorFlow is using. I know there's other ways to do this type of summation and get a more accurate result, but we know it's more accurate than whatever the standard library was giving us. And we also can observe that the standard library does take a wee bit longer than using TensorFlow. So hopefully this has convinced you that just using TensorFlow for Scala for numerical algorithms is not only faster, but it's also safer than doing the same thing using Scala standard collections. And there are other options available, but as soon as you're adding another option, as in importing another library to your project, you've committed to importing another library beyond the standard collections. So really, you should be making a choice between multiple different providers of things that can get you better numerical programming. And I highly recommend using TensorFlow for Scala. It's quite nice. That's all I'm going to go over now. Next time, I think we'll go over pulling it into Almond, because we want to try out doing plotting in Almond when we're getting these results for tensors. It's going to be a bit easier. And also I want to talk about the NumPy-like indexing and slicing, reshaping, creating tensors, and other operations. Until then, I hope you have a good day.